Hey students, Professor Nugent here. We're going to continue our discussion of homoskedasticity and heteroskedasticity in this video. So far, in chapters 4 and 5 up to this point, we have implicitly assumed that the OLS residual U might be heteroskedastic, without really saying so. Right? We have assumed it implicitly. Recall our three least squares assumptions that the expected value of U given x is 0, right? We cannot use x to predict the value of U, or the factors contained in U are unrelated to x. That the observation xi, yi for observations, or for I is equal to 1 through n, they are independently and identically distributed. And we have that large outliers are rare. Now, heteroskedasticity and homoskedasticity concern the conditional variance of U given x. Because we have not explicitly assumed that our errors demonstrate homoskedasticity, we have implicitly allowed for heteroskedasticity, and the standard error of beta 1 hat, the standard error of beta naught, these things are the heteroskedastic robust standard errors. Okay, so we have implicitly allowed for heteroskedasticity. Now you can prove if in fact our errors are homoskedastic, that ordinary least squares has the lowest variance among estimators that are linear in y. And this is a result called the Gauss-Markov theorem. And we're going to come back to this in the next video. But this is a very important result that shows that OLS is the best linear unbiased estimator, given that the assumptions are satisfied. And we will come back to that. Another consequence or benefit of errors being homoskedastic is that the formula for the variance of beta 1 hat and the OLS standard error, it simplifies. So the general formula that we have been working with is what I'm circling now, that the variance of beta 1 hat is equal to, we'll call this the variance, we've defined this variable vi over n times the square of the variance of x. This is the general formula.
So this general formula, this is what you find in equation 4.19, right? This is the variance of beta 1 hat, and this is the heteroskedastic robust standard error. But if the conditional variance of U given x, this thing is equal to sigma squared U, in other words, it's constant, then equation 4.19 is going to simplify to this equation here. Okay, so the variance of U given x, we get that sigma squared U over n times sigma squared x. This is the simplified variance of beta 1 hat when the OLS residual is homoskedastic. We still have that the variance of beta 1 hat is proportional to the variance of x. Okay, that is still the result, and it is also still inversely proportional to the sample size. So these key characteristics of the variance of beta 1 hat are still here. It is just simplified to the ratio of the variance of U over n times the variance of x. Okay. And if the errors in fact are homoskedastic, along with this homoskedasticity only formula for the variance of beta 1 hat, we have homoskedasticity only standard errors. So the standard error of beta 1 hat is given by this formula, which is the square root of 1 over n times 1 over n minus 2 times the sum of the squared residuals all over 1 over n times the sum of xi minus x bar squared, right? And this is the sample variance of x, and that's the sum of squared residuals. Now, some folks, like people who are working with Excel, might find this formula to be simpler than the heteroskedasticity robust standard error. But it will be wrong unless the errors are homoskedastic. And if we use the homoskedasticity only formula when our errors are in fact heteroskedastic, then it is likely that our standard errors will be too small. They will be biased downwards, which is not useful for making good statistical inference about our coefficients. Okay? We want to make good statistical inference. So our homoskedasticity only standard errors are valid only if the errors are homoskedastic. The usual standard errors, to differentiate the two, it is conventional to call the usual standard errors heteroskedasticity robust standard errors because they are valid whether or not the errors are heteroskedastic. We can use the heteroskedasticity robust standard errors if we have data for which the OLS residual demonstrates homoskedasticity. There will be no penalty. The main advantage of homoskedasticity only standard errors is that the formula is simpler, so it's easier to program. Like if we have Excel and we're doing our own programming, or any kind of software program where we're programming ourselves. But the disadvantage is that the formula is only correct if the errors are homoskedastic. So typically, we want to always use heteroskedasticity robust standard errors, especially for using stata, because all we need to do is write comma robust. So there's very little cost to us in using heteroskedasticity robust standard errors. However, there is a cost to using homoskedasticity robust standard errors, which would be the case if we did not include comma robust after our regression. Okay, in that case, we would be using homoskedasticity robust standard errors, and if in fact our data represented heteroskedasticity, then our standard errors would be incorrect. They would be biased. There's a good chance they would be biased downward, and we would not be making good statistical inference. Let's think about some practical implications. The homoskedasticity only formula for the standard error beta 1 hat and the heteroskedasticity robust formula differ. So in general, you're going to get different standard errors using different formulas. Okay. The homoskedasticity only standard errors are the default setting in regression software like Stata. To get the heteroskedasticity robust standard errors, we have to override the default. And to do that, after we write our regression, right, like reg y, x1, we may have an x2, x3. That's coming next chapter. We need to write comma robust. So if we do not override the default and write comma robust, have Stata calculate our heteroskedasticity robust standard errors, and there is in fact heteroskedasticity, our standard errors and our test statistics and our confidence intervals, they're all going to be wrong. It's all going to be wrong. The whole thing. And typically we find that, as I've been saying, homoskedasticity only standard errors, they're too small. So we're not making good statistical inference. Let's look at an example. Here we are calling on Stata to produce the heteroskedasticity robust standard errors because we have written comma robust after our regression. So we have regression with robust standard errors, and these are our heteroskedasticity robust standard errors. Okay, if we do not do this, then Stata will compute homoskedasticity only standard errors. Our standard errors will be too small. There is a, if you have a standard error that is too small, then you are more likely to reject the null when perhaps we should not be rejecting the null. So you are opening yourself up to type 1 error. Okay. All right. The bottom line, if the errors are homoskedastic or heteroskedastic, let's just use the heteroskedastic robust standard errors. Okay, there is no penalty really for doing this. All you have to do is write comma robust. If the errors are heteroskedastic, you use the homoskedasticity only formula for standard errors. Your standard errors are going to be wrong. They're going to be too small, and we're not going to be making good inference. In the next slide, in the next video, we're going to discuss some additional theoretical foundations.